Hello, today we will discuss about bipolar junction transistor. I will cover the structure, energy band diagram, current voltage characteristic, working principle and biasing of bipolar junction transistor. The working principle of transistor is similar to water tap. Whenever we need the water, we can open the tap, and whenever we don't want, we can close. By using the tap, we can control the water flow. Similarly, in transistors, we can use for two applications. One is for switching, another one for amplification. In switching, we have minimum current, that one is called the off state. The current is minimum, we call this one is the zero state. And the another state in that current is large, we call this one is the one state. We can use this one for digital logic applications, and in second application we can use for amplification. So, small change in third terminal create the large change in output between 1 and 2. So, here we can use for the amplification, and this one is depend on how much we have current gain. So, first transistors was fabricated in 1947 at Bell Laboratory, USA by three great scientists, Bardeen, Burton and Shockley, and they have demonstrated this first transistor on germanium semiconductors. This one is the transistor is a 3-terminal device, and currently these transistors are fabricated on silicon or gallium arsenide. So, in first figure you can see the photo of these great scientists, and second, this one is the first transistor was fabricated by these three scientists. So, now we will understand the working principle of these bipolar junction transistors. So, if you will take simply the PN junction, here you can see in the left hand side in the figure, this one is the simple PN junction, and now if you will attach with the battery, and here this junction is in the reverse bias. So, current is there in the reverse bias, this one is very small current, and here in middle figure you can see the current voltage characteristics. So, this diode is in reverse bias, and reverse bias current is very small, generally in microampere. Now, if you will take some optical source, and the energy of these photons is greater than the band gap of this semiconductor. So, these photons will be absorbed in the depletion region and nearby this depletion region, and will create electron and hole, and due to this electron and hole there will be a current conduction, and our reverse bias current is there, this will increase, and the magnitude of this current is depend on the intensity of light source. So, if we are increasing the intensity, our reverse bias current will increase with intensity. So, basically this reverse bias current we can control by the intensity of this light source. So, same concept if you will take in the right hand side figure, if you will take some hypothetical hole injector, and if you inject these holes near to the depletion region in N side. Now, electric field is there, this one is from N to P. So, these holes will move from N side to P, and we are injecting near to this depletion region. So, when we are injecting these holes will contribute in the current, and reverse bias current again can be controlled by these hole injectors, and reverse bias current is depend on the how much concentration we have injected near to the depletion region. So, this hypothetical hole injector we can replace in the practical devices by the P plus N junction. So, in the transistor we have one reverse bias junction. In the below figure you can see one reverse bias junction, this one is the NP junction, and we are connecting this hole injector by using the P plus N junction, and the output current can be controlled by the input current, this one is the IE. So, in the right hand side you can see the current voltage characteristics, this is the IC current, and voltage is between base and collector. So, basically in the transistor we have three terminals. First one is the emitter, we are injecting the carrier from emitter to base, and second one is the base, and third one is the collector. So, in the collector we are collecting these injected carriers by the collector. So, here collector current we are controlling by the emitter current. So, if you see transistor having the 3 layers and 2 junction, one is P plus N junction, another one is NP junction, and the middle region is there, this one is very thin. So, injected carriers can easily move from this region and can reach the collector. So these three regions are called emitter, base and collector, and the width of base region should be very small, and this should be smaller than the diffusion length of these injected carriers. Now we can divide these bipolar junction transistor into two categories. First one is the PNP and second one is the NPN. So in PNP transistor, our emitter is P doped, base is N doped, and collector is again P doped. So this one is called PNP, and we have three terminals, one from emitter, collector and base. And here in the right hand side you can see the circuits symbol, and in the circuit symbol this carriers are injected from emitter to base. So current flow is from emitter to base. Other type is NPN transistor. In NPN transistor, electrons are injected from emitter to base here. So current flow is in opposite direction from base to emitter. So here in the circuit symbol you can see the arrow, this one is from base to emitter. So if arrow is from emitter to base, that means this transistor is PNP. If arrow is from base to emitter, that means this transistor is NPN. So basically in the circuit symbol this arrow is indicating the direction of current flow. Now we will come on the energy band diagram. We will try to understand the carrier flow, how these carriers are moving, this one. So here in figure A you can see this PNP transistor, and in between, because we have not applied any bias, our transistor is in thermal equilibrium. Emitter is highly doped, so here depletion width between P plus and N, this one is small compared to the base and collector depletion width. And if we see the charge distribution here in figure B, we can see the charge distribution, and this one is similar to the PN junction we have discussed earlier. And by using this doping we can calculate the electric field. So electric field P plus N junction, this one is in the minus direction, we can calculate the maximum electric field, and in NPN this one is in opposite direction. And similar to PN junction, here we can make the energy band diagram. So our Fermi level in thermal equilibrium, this one is at constant position, emitter is P type, Fermi level is close to the valence band, again in base is N doped, so Fermi level is close to conduction band, and in collector this one is again P doped, so Fermi level is close to valence band. In thermal equilibrium our Fermi level is constant, and other conduction band and valence band we can draw this energy band diagram. So now if we will apply the biasing, then what will happen to these energy bands? So here we will discuss the active mode. In active mode our first junction is in forward direction and second junction is in reverse bias junction. So here in figure A you can see the biasing, how we have applied this one. Now when we are applying forward bias, our depletion width is decreasing. So here in figure B you can see the charge distribution. So when depletion width is decreasing, our electric field is decreased, and in the reverse bias depletion width is increased, electric field is increased. Under this biasing, holes are injected from emitter to base, and base is N-type doped. Few holes will recombine, but maximum hole will reach to the collector and will contribute in collector current. So here in figure D you can see the energy band diagram under the biasing. Based on biasing, we can divide our transistor operation in these four categories. If first transistor is in forward bias and second junction is also in the forward bias, in that case we call our transistor is in saturation state. So if little bit if we will change our input current, output there will be a large change in output current. Second mode is active mode. In this active mode, first junction is in forward bias and second one is in the reverse bias, and this mode mostly we will use for the amplification purpose. In third mode, our first junction is in reverse bias and second junction is also in reverse bias. So in this condition we have very small current, and this one is called the cutoff region. And the fourth one is the inverted. This one is similar to the active mode. Generally this mode we will not use for practical applications. Output current is controlled by the minority carriers, and here you can see the distribution how is the minority carrier distribution. This we can calculate similar to the PN junction we have calculated in the forward bias and reverse bias the minority carrier distribution. So, if you see in the emitter, the minority carriers will decrease with the distance, and in base region this will also exponentially will decrease in PN junction, but here our width is very small, our base width is very small, less than the diffusion length. So, here we can assume this one our linearly these carriers are decreasing. And in third region collector, this one is again similar to the PN junction in the reverse bias. If you see in the saturation case, both junctions are in forward bias. So, in the base region we have very high minority carrier concentration. In third case cutoff, the minority carrier distribution in base region is very small. So, the current is there in cutoff region, very small current. So, here we can calculate the different components. If you see in this figure, the maximum these holes are injected from the emitter, because emitter is highly doped, we have to dope. Maximum number of holes can be injected from emitter to base. So, few holes are recombined in the base region and maximum this one is reached to the collector. So, our emitter current IE is equal to IEP, this one is current due to holes, IEN, this one is current due to electrons. Electrons also injected from base to emitter, but this contribution is less, and our collector current IC equal to ICP plus ICN. Again here the maximum contribution in collector current is due to holes, and IB, this one is IE minus IC. So, basically we can calculate these three currents, emitter, collector and base currents, by using these relations. Now, I will come on the biasing of bipolar junction transistors. So, we can bias in three different ways. First one, here you can see the common base. Common base means between input and output our base is common. So, here our input voltage we are applying between emitter and base, and output is between collector and base, and our base is common between input and output. Here we can see the input current is IE and output current is IC. This mode is called the common base configuration mode. Second mode is the common emitter configuration. In this one our emitter is common. So, input current voltage we are applying between base and emitter, and output is between emitter and collector. Similarly, in the common collector, collector is common, input we are applying between base and collector, and output is between collector and emitter. So, here one by one we will discuss these three configuration, and mainly we will focus on the common base and common emitter, because this common collector mostly we are using only for matching purpose. Current voltage characteristic of common base configuration. So, here you can see we have applied input bias between emitter and base, and output we are taking between collector and base. So, our output current is IC and input current is IE. Now, if you are changing in input current, output current will change. So, initially if you will take IE is 0 open circuit, in that case we will get very small current. Now, if we are increasing IE, with increasing IE our IC current also will change. Output current we can control by using the input current here, and now we will derive the relationship between output current and input current. So, here we define common base current gain. This one is the ratio alpha 0 equal to ICP. This one is the current, collector current due to holes upon IE. IE is having two components, IEP plus IEN. So, current due to holes plus current due to electrons, and we can rearrange this equation. I alpha 0 equal to IEP upon IEP plus IEN multiply by ICP upon IEP. In equation 1, the first term in right hand side we can define, this one is the emitter efficiency gamma IEP upon IE, and second term we can define the base transport factor, this one how many holes are recombined and how many holes reached at the collector. So, this is called the transport factor alpha t equal to ICP upon IEP. So, now our common base current gain alpha 0 is equal to gamma alpha t. So, this one is depend on the emitter efficiency and base transport factor. So, now our output current IC we can write ICP plus ICN, and ICP we can write alpha t IEP. Again we can rearrange these equations, and here if you will multiply by gamma and divide by gamma this one. So, final equation we will get our collector current IC equal to alpha 0 IE plus ICN. This one is the collector current due to electrons, and this one is very small current. So, to calculate this one we can open our input. So, when we open our input circuit, IE is equal to 0. So, our now IC is current is, this one is the leakage current between collector and base when emitter is open. So, we can write this equation IC equal to alpha 0 IE plus ICBO. If you see our common base current gain factor alpha 0, always this one is less than 1. So, by in this configuration we will not get the amplification, because ICBO, this one is the leakage current very small, generally this one is in microampere, and alpha E is in milliampere. So, here because alpha 0 factor is less than 1, this one is close to 1, but always this one is less than 1. So, in this configuration we will not get the amplification, only we can use for the switching application. So, now we will come on the common emitter configuration. So, here our input current is IB and output current is IC, and in figure B you can see the current voltage characteristics. Generally IB current is in microampere and our output current is in milliampere. So, here input current if will change in microampere, output we are getting in milliampere change. Basically by using this configuration we can use for the amplification applications, but here again we will derive the relationship between output current and input current. So, now here output current is IC and input current is IB. So, in this equation you can see IC equal to alpha 0 IE plus ICBO. We have derived this equation in common base configuration. Now, we can write IE is equal to IB plus IC. So, rearrange these equations and we can write IC equal to alpha 0 1 minus alpha 0 IB plus ICBO upon 1 minus alpha 0, and here we can define one more factor. This one is called common emitter current gain beta 0, and beta 0 is equal to alpha 0 1 minus alpha 0, and leakage current here we can define again. Our input circuit is open, that means IB is 0. We can define the leakage current ICEO is equal to ICBO upon 1 minus alpha 0. So, here our output current is IC is equal to beta 0 IB plus ICEO. So, leakage current is very small. Now, here the output current is depend on the beta 0. So, here if you will take example, our common base current gain factor alpha 0 is 0.99. Now, if you will calculate the beta 0, this one is 99. If alpha 0 is 0.998 beta, we will get 499. So, now our beta factor common emitter current gain factor is more than 1, this one is 99, yeah 499. So, in this configuration we will get the amplification. If you will small change in base current, this will multiply by 99, yeah 499, this one is depend on the again alpha 0, but here our output current we can amplify by 99, yeah 499 times to our input current. So, we can use this configuration for amplification applications. Now, I will discuss one more important effect. This one is called the early effect. So, if you see in the common emitter configuration, ideally we should get the horizontal our output current. Here you can see in the blue, in the ideal case we should get the horizontal this IV plot, but we are not getting the horizontal. Here we are getting one slope, and if you will extra plot these slopes, we will merge on a single point. This voltage is called the early voltage. This early effect we can explain by using the base width. In our calculation we have assumed that base width is constant, this one is not changing with biasing. But if we see the practically, when we are increasing the voltage, our base width is also modulating this one, and mainly this base width modulation is due to the collector base depletion region. When we are applying the reverse bias, this width is increasing, and now our this base width, neutral width, this one is not constant, this one is changing with biasing, and due to this one we are getting this one slope in the output current. So, with applied bias, our base width is there, this one is changing, and when we are applying more voltage, base width is reducing this one, and due to this base width modulation we are getting a slope in our output current. So far we have discussed the DC behavior of bipolar junction transistors. Now we will talk about the AC response of BJT, and here in left hand side figure you can see the biasing diagram. Here we have applied this one small signal at the input between base and emitter, and output we are measuring between emitter and collector. So, our output current is there, this one is changing with input current. So, here you can see the IV diagram, output current and voltage diagram in right hand side figure. Here we have connected a AC voltage source between emitter and base, and we are changing here small change. When we are changing this voltage in the half cycle, this one is positive, another half cycle this one is negative. So, our base current is also changing. So, here inside this figure in right hand side you can see the base current, this one is changing in micro ampere range. So, here this base in the positive cycle change is around 4 micron, and again in negative this change is in minus 4 ampere. So, now due to this change in input current, how much change is there in output current? So, here we can this one extrapolate these lines and we can see the our collector current. So, collector current is changing in the milliampere. Now, our signal is that this one is very weak, this one current is in microampere, but our output current is changing in milliampere. So, here we can use this configuration for the amplification purpose. Today we have discussed about the structure of bipolar junction transistor, working principle, current voltage characteristic, energy band diagram, and different configuration, common base, common emitter, and we have calculated the output current, collector current, how this one is changing with input current, and finally we have discussed the early effect and AC response of bipolar junction transistor. I hope you have enjoyed this lecture. Thank you very much.